Welcome to all of you this morning. Thank you for your overwhelming response to this two-day meeting, Predictability in General Relativity, which celebrates the contributions of Professor Yvonne Choquet-Bruhat to general relativity. It's indeed a great privilege to be able to celebrate her centenary year in this manner, and I thank in particular Professor Daniel Choquet for conveying our wishes to her, which also comes packaged in the guise of this conference. Generations of students of general relativity from all over the world have learned the initial value formulation, perhaps not always realizing the contributions of Professor Choquet-Bruhat. Indeed, it is her seminal work that helped lay the foundation for our modern understanding of general relativity. Her depth and breadth of interest and her humility are well captured in the foreword to her 2009 Oxford monographs titled General Relativity and the Einstein Equations, where she states, and I quote from that book, "This book is essentially concerned with mathematical problems about the Einstein equations and their sources. However, I never forgot during the 60 years I worked on general relativity, with some incursions into other subjects, that it is a physical theory. I remained interested in the interpretation of new observations and experiments which were made possible by the extraordinary progress in telescopes, satellites, particle colliders, and nanotechnologies, and which confirmed more and more the physical relevance of general relativity. I also remained fascinated by the remarkable theoretical developments which have considerably extended the scope of general relativity as a theory of gravitation, as was in fact the hope of Einstein, and are a subject of active research." In this book, she says, "Lack of space and time, and also my incompetence, have prevented me from including these new experimental and theoretical fields of research in this book." I think that's very telling and very interesting forward to this field and her own contributions. I reiterate, it is her seminal work that has helped lay the foundation for our modern understanding of general relativity. This in turn has had a profound impact on mathematical and numerical relativity, as well as in different approaches to quantum gravity. We are very lucky that all of these broad topics will be represented in this meeting by the leading experts in these areas. We have an outstanding list of speakers, as you all know. They will walk us through recent research in areas which have been deeply influenced by the work of Professor Choquet-Bruhat. This meeting has had an overwhelming response. Over 240 participants have registered from all over the world. So we have a truly global audience of general relativists with us today. Thank you very much. A few words about the hosts of this meeting before I pass it on to Professor Tarun Sauradeep, our director. Although online, this meeting is held jointly by the Raman Research Institute, Bangalore, as well as the International Center for Theoretical Sciences, also in Bangalore, under the aegis of the Indian Association of General Relativity and Gravitation. RRI, that's the Raman Research Institute as we know it, was founded in 1948 by the Indian physicist and Nobel laureate Sir C.V. Raman. Last year, the institute celebrated its 75th anniversary, which included 5 very well-attended international conferences. Research, both experimental and theoretical, is carried out in diverse areas of physics. Relevant to this meeting is its strong tradition in general relativity, which continues into the present. The International Center for Theoretical Sciences, ICTS, is a multi- and interdisciplinary center of the Tata Institute of Fundamental Research. Established in 2007, ICTS is modeled after peer institutions such as the KITP and the ICTP. Apart from its focus on multidisciplinary research and science outreach, the ICTS is well known for hosting several international programs each year. These bring together physicists, mathematicians, and biologists from all over the world to work together to solve the most challenging questions in science. The meeting is also held under the aegis of the Indian Association for General Relativity and Gravitation, of which I am the outgoing president. It is therefore wonderfully satisfying to end my term with this meeting. This conference adds to the recent initiatives taken by the IAGRG, namely the addition of new schools and workshops to the traditional menu of biennial meetings. Recently, a working group on gender was constituted at the IAGRG, a much needed step towards equity. As with all such efforts towards equity, it is equally important to bring to the fore the exceptional scientific research that can come from diversity and the practice of inclusion. It would be fair to say that this conference is an embodiment of this in multiple ways. A few practical words before we start, but before that, let me please invite Professor Tarun Sauradeep to say a few words. He's the director of the Raman Research Institute.
Thank you, Sumati. It's my honor and privilege to welcome you all to this wonderful meeting celebrating the centenary of Professor Yvonne Choquet-Bruhat, a very well-known figure to anyone who has had a brush with general relativity. And I'm very happy to say that this is being held at an institute which has really over decades been a very important center of general relativity research, starting with Professor Vishweshwara, Bala Iyer, and now we have Sumati and Madhavan, Sumati Surya and Madhavan Varadarajan. And I'm very happy to say, and we're delighted that last year we have a new faculty, general relativity field broadly, Karthik Prabhu. And it gives me immense pleasure to see Sumati and Karthik being the organizers of this meeting. And I'm sure this means a lot towards keeping this amazing field alive. I mean, I'm personally indebted to general relativity and the lectures I heard in my undergraduate for moving into physics. Although later I have worked more on applied aspects of general relativity cosmology. But, I believe, it's very important to really understand where the subject stems from. And Raman Research Institute has had the tradition of being an institute which has, not just run after the latest fashion, but has built deep roots into any area that it has grown. And that is over multiple areas. And today I'm, here, very happily looking at how this area of gravitation and possibly in the years ahead how gravitation and astrophysics will, grow firm roots in the institute. So I'd like to welcome you all. I already commended Sumati and Karthik and Prayush and Shalab on the amazing speakers and the wonderful organization. I mean, personally, I've done that to them, but on the other hand, I mean, I must say I'm very grateful that people have taken great efforts to stay up late or, stay up early to join from across the globe. And I'm sure this is going to be an exciting meeting, something from where not only the participants here, but those who would follow the recorded lectures would, benefit a lot. Finally, I should say it's an amazing day for Raman Research Institute because today is the National Science Day, which is celebrated in India to celebrate Raman's announcement of the Raman effect. Which is, in Indian context, the Nobel Prize winning work in the 1930s, 20s and over the 80s. So, which also unfortunately means that I'm not going to be able to attend many of the talks because of various commitments to the National Science Day which is happening outside. If I turn my camera, you would see that we have a huge pavilion and an open gallery for people to come and celebrate. So I'm glad relativists are celebrating National Science Day in this fashion by kind of uh, you know felicitating one of the leaders of the field. And Yvonne Choquet-Bruhat, Sumati has given an introduction. All I can say is my certificate for being a relativist is her book is on my bookshelf, although it's not clear, whom it belongs to between me and my spouse, but it is something amazing to have such a meeting. Thank you so much, and have a great day.
Thank you so much, Tarun. I will just state a few practical words before we start. We have requested that all questions be sent in the chat box to the host called questions. We will ask as many of these as possible given time constraints at the end of the talk. We're also recording the talks, and these should become available as soon as possible on the website. And so it is a great delight, without further delay, to be able to introduce and invite our first speaker of the conference, Professor Abhay Ashtekar, who is no stranger to the Raman Research Institute. He himself has worked here in the past, and of course visited multiple times. Professor Ashtekar from the Penn State University is the Atherton Professor, the Evan Pugh Professor Emeritus, the Eberly Chair Emeritus, and past Director, Institute of Gravitation and Cosmos at the Penn State University. His talk is titled The Many Faces of the Initial Value Formulation, a tribute to Professor Yvonne Choquet. So please, Professor Abhay Ashtekar, please, you may begin your talk. I hope it's all, yes.
Okay, you can hear me? Yeah, and I think you can see my screen. So what I would like to talk about is really these many faces, and in particular, 3 of them that I will discuss in detail of the initial value formulation. Madame Choquet has been an inspiring scientist to all of us for decades. But there are aspects of her personal life that illustrate even more profound qualities. I will begin with a deeply moving anecdote in her early life that enhanced my admiration for her person in an immeasurable way. In the main part of the talk, I will discuss these 3 aspects of initial value formulation of general relativity that encompass dynamical black holes, null infinity, and the generalization of the formulation provided by the connection variables of loop quantum gravity. The organizer specifically asked me to include something about loop quantum gravity, and the 3rd part will be that. The first of these emphasizes constraint equations, the second dynamical equations, and the 3rd provides a generalization of the standard initial value formulation that can enable us to evolve across certain singularities going beyond the standard Cauchy problem. Okay, so let me begin with the very first part, the 0th part, which is homage to Madame Choquet. It's a pleasure and honor to participate in this celebration of Madame Choquet's 100th birthday. She has been an inspiring figure to me since I studied her early work on Einstein's equations as a PhD student almost 50 years ago. Already then, she was a legend and as an early pioneer, exploring these equations using rigorous methods from geometrical analysis. Indeed, papers she wrote already in the 1950s are such towering landmarks that they continue to be important and cited even today. My admiration for her work grew over subsequent years as I came to know more about her deep contributions. I then had a privilege of being her colleague at Jussieu campus in the 1980s in Paris as a professor in Paris. Do you see my screen or?
No, it has disappeared. For some reason, the screen sharing just stopped. Can you try that again? Sorry, I'm not sure. Yes, we can see your screen, but you can open your talk again. Yes, that's okay.
Great. Okay, so yeah, so I then had a privilege because I had a professorship following actually Madame Tonla's chair in gravity was open for a long time, and that was offered to me in the 1980s. And even though we were in Paris, our path did not cross every week. It was not regular. But a warm welcome to Paris and scientific discussions at seminars and in Journey Relativist which is the annual meetings of relativity in France, were among the highlights of my academic life in France. The Paris academic scene was not very easy for me to navigate, and I'm grateful to have had a guide in Madame Choquet during those years. In the subsequent 20 years or so, my own research was focused more on quantum gravity, and even my contributions to classical general relativity have been more at the interface of geometry and physics rather than geometry and analysis. Nonetheless, I found Madame Choquet's work inspiring. Her book, Geometry, Analysis, and Physics, has been one of the most used books on my shelf in my office since the late 70s. When she was awarded Danny Heinemann Prize by the American Physical Society in 2003, I wrote to her expressing my sentiments on hearing the news. Most prizes honor the recipients, but on rare occasions, it is recipients who make the prize more prestigious, and that was indeed the case for the Danny Heinemann Prize. In more recent years, I had the privilege of interacting with Madame Choquet in person at a KITP workshop in Santa Barbara, at a Marcel Grossman meeting in Rome, and the celebration of the 100th anniversary of general relativity in Berlin. On the Santa Barbara campus, we watched with great admiration as she rode her bicycle in a cheerful, carefree manner. She had not changed or all those years. There was the same kindness radiating from her, the same mathematical rigor, and the same simplicity in her demeanor, providing us with a role model on how to live a productive and fulfilling life with inner serenity. And then over the last 5 years, I came to learn about her life as a student in occupied France. So in August of 1944, Yvonne's father, Choquet-Bruhat, he was a physicist and a deputy director of the Paris École Normale Supérieure. And he refused to cooperate with the occupying German forces, and particularly Gestapo, who wanted the list of certain students and their whereabouts, who Gestapo suspected as being leading underground movement against them. And but Professor George Choquet really refused, and therefore they arrested him. Not only him, but then the same day they arrested his wife, Yvonne's mother, Bertha Bruhat, and threatened to kill her the following day if Yvonne's father did not cooperate, literally shoot her in front of her father. Young Yvonne then went to Gestapo headquarters and pleaded to allow her to take her mother's place. When I read this, my heart melted and there were tears in my eyes. This was a new whole dimension of Madame Choquet that I knew nothing about. You see, I mean, there are several very celebrated people who left Germany. Einstein never forgave Germany and never went back to Germany. Even Jacob Bekenstein never stepped foot in Germany afterwards because of the Nazi occupation and what happened during that time. But Madame Choquet's heart was so big that she forgave all these things, and she lived serenely. She has cooperated with the German physicists, mathematicians, without any malice, without any negative feelings that are in her heart. And to have this ability is really incredibly rare. So to have made such deep contributions to mathematics and to attain inner serenity in spite of this, in spite of enduring such traumatic events early on, made my already tremendous admiration and respect grow 1,000-fold. What a remarkable life you have led, Madame Choquet. I feel fortunate to have known you in person. Okay, so after this homage, I would like now to begin with the technical part of the talk. And the first part is constraint equations as applied to what is known as dynamical horizons. So let me explain all these things a little bit. So constraint equations is a largely work with Badri Krishnan and with Badri Krishnan, who is now in the Netherlands, in Nijmegen. So as we know that we got a notion of event horizon in general relativity, and here is a typical stellar collapse. Gravitational radiation is emitted if it's not spherically symmetric. And then event horizon develops, and then we got scry minus and scry plus. And what we do is really we look at past of scry plus up here, which is this region up here, and we look at its future boundary, and that is the event horizon. And what is included in the whole space-time minus this past of scry plus is the black hole region. And as you can see, all light cones from here will go into singularity. Nothing escapes out to infinity. So that is why it is so significant. And another reason why it is so significant is because of the laws of black hole mechanics hold for these stationary event horizons, for zeroth and the first law of black hole mechanics. And for dynamical black holes, we got the second law, the famous law of Hawking, which says that the area of a black hole cannot decrease. But there are also limitations. First of all, you need asymptotic regions, either asymptotic flatness or asymptotically distributed or anti-distributed space-time. If the universe is spatially compact, we don't have the notion of an event horizon, for example, of this event horizon, which defines a black hole. We don't have the notion of black hole event horizons. And the event horizons are not smooth. A relatively recent paper of Gaudieu and Rial sort of go into some details about it. And then the area role is only qualitative. It's very important, but it really is qualitative. And this is illustrated here by the Vaidya solution. So here you got scry minus, here you got scry plus, and there is some null fluid which falls in from scry minus. It's a null collapse, and that makes an event horizon here. Here is a past of scry plus, and here is the boundary, and that is the event horizon, and that's what we got up here. But in this entire region of space-time to the past of the matter, we just have Minkowski metric, flat space-time. So as you can see, the event horizon starts forming in the flat Minkowski part of the space-time, and in fact grows even in this flat space. So this growth of the event horizon area, it's true, it always grows under the standard assumptions that are made in the theorem. But the statement is that those standard assumptions involve energy condition, which is violated in the black hole evaporation process. But in the classical relativity, with those standard assumptions, event horizon area always grows. But it is not really related to any physical process. Nothing, absolutely nothing is happening here. And yet the event horizon is growing in this region up here. In fact, there can be an event horizon in the room that you are contained in the room that is you are sitting in and growing at this very instant of time in anticipation of a collapse that would happen, a million years from now. And you would not know. There's nothing here, and yet the event horizon will be growing. And therefore, this is the teleology that I have up here, namely that you really need to know the entire history of space-time, and if it has an asymptotic region, only then can we talk about the event horizon of a black hole. Well, the dynamical horizon is an example of a quasi-local horizon that though they were introduced in order to overcome these limitations of the event horizon. So dynamical horizon, I'm simplifying in this talk a little bit, but I'm giving references at the end, and those references will have at least the list of papers from which you can start reading about the beginning of these notions and these ideas. So it's a space-like three-dimensional manifold, which is foliated by marginally trapped surfaces, such that this is wrong. Such that the expansion of the outgoing null normal is zero, and the expansion of the incoming null normal is actually negative. So that is the notion of a dynamical horizon. It's very simple. And dynamical horizons are routinely used in general relativity in the numerical simulations of black holes. That's what people mean by horizons in black hole. And for example, what one does is, here is an example of a dynamical horizon. So here time is running like that as usual, and space is, these are the spatial directions. And so what you have is a foliation in space-time. And on each leaf of the foliation, you find the apparent horizon, the outermost marginally trapped surface. And then the world tube of these apparent horizons is what is dynamical horizon up here. It is a space-like surface, so it has a time-like normal. So tau hat is equal to -1 up here. And of course, since it is foliated by these marginally trapped surfaces, there is also within the dynamical horizon a preferred radial vector, which is perpendicular to this dynamical horizon, which I also have normalized up here. And I'm going to be denoting the three-dimensional dynamical horizon by this letter H up here. So S0 and S are two illustrative examples of marginally trapped surfaces which foliate the dynamical horizon. Now, because it is space-like surface, and for simplicity, let me say that suppose that there is no matter falling across it. In fact, no, we are allowing matter to fall across it, but I'm going to assume Einstein's equations. So we got constraint equations, which is really the constraint equations which hold on this space-like surface. So these are three-dimensional space-like surface in the space-time, and therefore constraint equations hold. I got the intrinsic metric QAB, and I got the extrinsic curvature KAB on this dynamical horizon up here. And I got a scalar constraint, and I got a vector constraint up here. The scalar constraint says that the richest scalar of this metric minus this combination, quadratic combination of this extrinsic curvature, is equal to the energy density. Oops, there are many typos. I didn't realize this. The extrinsic, So this is the stationary tensor, except that I've taken into account, removed the part which comes from the possible cosmological constant that may be present, a possible cosmological constant that is may present, and this tau hat is a unit normal. So this really is the energy density, including this cosmological contribution, if you like. And then we got here the vector constraint, which is really our diffeomorphism constraint, which says that the KAB minus KQAB is its divergence is given by the momentum density of matter. In this equation, because the cosmological constant term has a metric in it, and since I got a vector which is perpendicular to the surface and a projection operated into the surface, T bar here is the same as T. So I got this foliation. So I got three elements, namely, we got scalar constraint, we got a vector constraint, and we got foliation of this three-dimensional surface by marginally trapped surfaces up here. And this condition just transforms and says that, in fact, the extrinsic curvature and the metric, they're not completely independent, but in fact, the three-dimensional trace of the extrinsic curvature is related to the radial component of the extrinsic curvature minus this is the projection into the surface. This is the trace of the extrinsic curvature of these two-dimensional surfaces. So anytime you got orange symbols, they refer to two-dimensional fields up here. So this is an identity, this is just equivalent to that. So we just have these three equations, and these three equations have incredibly strong physical consequences. So what we're going to do is to take this linear combination of the field of these constraint equations up here. I'm just looking at the left-hand side, and I'm looking at the left-hand side of these things and this particular linear combination. Now, in this case, you can just work with these three assumptions and show that this combination is equal to the two-dimensional richest scalar of these surfaces minus the shear square of these surfaces, and the shear is defined by taking the derivative of the outgoing null normal and projecting it into the two spheres. Again, tilde is always into the two spheres. And then there is a vector zeta, which is the mixed component, mixed projection. One of the indices, namely A or B, is projected into the two sphere, and the other index is projected perpendicular to sphere along this vector field R hat that I got up here. So this is just a fact, you have to be careful to doing this calculation, but it's a simple fact up here. And now if I integrate these equations, this linear combination with this linear combination, so the left-hand side is integral of this, and the right-hand side would be the integral of these two terms up here. And I'm going to integrate it between two surfaces, such as S0 and S. So I'm integrating on this portion of the dynamical horizon, this three-dimensional portion of the dynamical horizon. That's where I'm integrating. And when I integrate that, I just find that the Gauss invariant of the two spheres, here I've drawn two spheres as though they're two-dimensional spheres, but they are just general compact two-dimensional manifolds so far. So the Gauss invariant of that divided by 8 pi, and this is equal to 1 if the topology is 2, and we'll talk about other topology in a second, times the radial area of these two spheres. So basically each of them has an area, and radius is just defined by 4 pi r squared. So that is the area radius of this thing. So the difference between the area radius, or the difference between the radii of these two spheres, is given by, on the right hand side, we got a positive definite quantity, namely it is a shear squared plus zeta squared. So it's really the square of this quantity. That's why and similarly this, the norm of this zeta up here, zeta is zeta a. So shear square is just this term, zeta is just this term up here, and integration by part this disappears, and this is a term which by integration gives me the Gauss invariant, which is out here, times R2 minus R1. So plus, of course, I got then the right hand side, which is the stress energy tensor, and then that is dotted with the unit normal to the sphere, which is this tau hat, which is the unit normal to the sphere, tau hat up here, that we got. And then that is the tau hat. And then n times L. N is a scalar, lapse up here. And the lapse is just defined by the norm of the gradient of this radius function that we got here. And it's positive. So this is positive. And therefore, this is the future directed causal vector. And so if you have stationary tensor, the usual stationary tensor, which is satisfies the energy condition, this is just the flux of the energy falling into the surface, and this quantity is positive, this quantity is manifestly positive, and therefore this quantity is positive. And therefore we got a quantitative relation here between the area increase and the geometrical contribution and the stationary energy contribution, the energy falling into the horizon up here. So really now we've got a physical reason why the area increases. And it's a counterintuitive fact that the evolution equation, the change in the area, can be thought of as being evolution equation that is coming from this constraint equation. And the reason is because normally we think of evolution in terms of these surfaces. You foliate space-time into this t equal to constant surfaces, t equal to t1, t equal to t2, and then we're marching along in time, and then this surface, the t equal to t1 surface intersects here, t equal to t2 surface intersects here. So we see what is happening in time up here. And now there are interesting implications of this topology. First of all, then this term is therefore has natural interpretation as a flux of gravitational energy which crosses the horizon. So if you have got gravitational radiation falling into the horizon, the energy across the horizon is given by this. You know, normally in general relativity, we don't have a formula for local flux of energy, but dynamical horizons are so special that we do have a formula, and the energy is falling across the dynamical horizons is always positive. Now, there are interesting implications of the topology of the marginal trapped surfaces. If lambda is bigger than 0, then this quantity if lambda is bigger than 0, then this quantity up here is a positive definite. And therefore, this is positive and this is positive. And then the statement is that, therefore, we can see that the area always increases up here. And therefore, we can see up here that, that the only topology that is allowed up here is really for which this I is positive, and that I positive means that the topology is S2. We know that R2 minus R1 minus R2 is positive, or rather, you should have been R minus R0 positive up here. And that we just know from the fact that the expansion is negative and the other expansion is positive. So we know that this is positive. That is a triviality. But the detailed relation between the change in the area and what is falling in is non-trivial. And furthermore, we know that if the lambda is positive, then this term is necessarily positive, and then therefore the topology here has to be that of a two-sphere. If lambda is equal to 0, then of course this term is greater than or equal to 0, and this term is greater than or equal to 0. So unless both of them vanish, again, I find that the topology has to be that of a sphere, because the Gauss invariant is positive for S2, 0 for torus, and less than 0 for higher genus. And it could be a torus, but in that case, it's an extremely degenerate case in which this has to be 0 and this also has to be 0. And if lambda is less than 0, then there are no restrictions. And this is also something that we expect, because we know that if lambda is less than 0, there are stationary solutions in which event horizons are not can have general higher genus topology, and therefore these dynamical horizons will asymptotically join on to those horizons. So there is a fascinating interplay between topology, differential geometry, and physics in this case. So let me now start with the second part of the talk, and that has to do with the evolution equations, and that has to do with null horizons and null infinity. The main message here is that dramatically different physics emerges from the same geometrical structures from Einstein's and conformal Einstein's equations. And you are going to hear about, in fact, some of the speakers who are in the audience will speak about the more geometric analysis consequence of Einstein's equation, and also on conformal Einstein's equations. So now what I would like to talk about is different kind of horizons, the horizons which are normally in equilibrium. So these are null horizons. So they are not growing. Their area is constant. So a non-expanding horizon is a null three-dimensional submanifold, and I call it H, of the space-time, such that, as before, it is expansion-free. If you have got a one foliation for a null surface, which is expansion-free, so K is a normal to the horizon, or here the horizon was space-like, and therefore the normal was time-like. Now the normal to the horizon itself is null, because the horizon is null. And so K is a normal to the horizon. And so the expansion is 0, so it's exactly a similar condition as before. But now the null normal is tangential to the horizon. And the second is that the Ricci tensor, this is a geometrical condition of the Ricci tensor dotted with K is proportional to K. So this is true only at the horizon itself. Elsewhere, there is no conditional geometry. So I'm not using so far field equations, either conformal or Einstein's equations. And so therefore, this really purely geometric conditions, and these geometric conditions have the following consequences. The first is that the intrinsic metric is null. I mean, that is just because I looked at null surface up here. And then the fact that theta is equal to 0 and this condition holds implies that the shear also vanishes, and if the expansion and shear vanishes, then in fact the two-dimensional metric that we got on the surface is actually constant. So here you've got a topology which is a S2 cross R topology up here, and along this K direction, the area of the horizon doesn't change. Then because of this property, it follows also that the space-time derivative operator can be pulled back to the manifold to give you an intrinsic derivative operator at dA on H. And this dA, of course, kills this metric dA of QAB equal to 0, QBC equal to 0 on the horizon. This hat means these equations hold just at the horizon. So that is, of course, true. But in fact, something more is true, namely that, because Q is actually a degenerate metric, there are infinitely many derivative operators which will kill it. But the statement is that the space-time derivative operator gives you a unique connection up here. And we can always choose a null normal, which is geodesic. So which I find the parameterized geodesics. And furthermore, we can always do it in such a way that, first of all, the null normal satisfies dA of KB is proportional to KB. Therefore, there's a one form omega, and we can choose it. The fact that K is geodesic means omega dot K is equal to 0. So it only has two components, if you like, this omega, and we can make it divergence free. And if you make it divergence free, then K bar is unique up to this constant rescaling. So given a non-expanding horizon, I can equip it with a null normal up to a constant rescaling, a unique one, for which decay of omega is equal to 0. So this equation also just follows from the fact that I got theta equal to 0. I got this is true and theta is equal to 0. This equation then will tell me that in fact decay of omega equal to 0. So omega is time independent. So the metric is time independent. The metric Q is time independent. The derivative operator defines a one form omega. By the way, this omega has information about rotation in the horizon, and this omega is also time independent. So it looks like everything is time independent. Then the non-expanding horizon equipped with this equivalence class, where dk is equal to omega, is said to be a weakly isolated horizon. And we can always make every non-expanding horizon canonically into a weakly isolated horizon. And now zeroth and the first law of horizon mechanics hold for any weakly isolated horizon. And therefore, they carry the connotation of representing black hole and cosmological horizons in equilibrium. And they have been called in the literature stationary, or essentially like the killing horizons. But it turns out that this is incorrect, because null infinity is also a weakly isolated horizon, and it is highly dynamical. There can be arbitrary amount of gravitational waves going across null infinity. And then how can this be, right? Because we got this connotation is stationary. And we saw, in fact, that omega is time independent. The metric is time independent. So what's going on here? How can Scry have a radiation on it? The boundaries boundaries of black holes in equilibrium and Scry have opposite connotations. The black holes lie in the strong curvature region. Scry lies in the asymptotic region. The equilibrium thing, there is no radiation across it. Scry, there is a lot of radiation across it. How can this be happen? So, is there dynamics in the geometry? We already saw there is no dynamics here. Is there perhaps dynamics in D? Well, part of D is omega, and part of D is omega because of that, and there is no dynamics for this omega. So, metric is time independent, and omega is also time independent. And then, because if you take a horizontal one form and operate by D on the horizontal one form is the one which is orthogonal to the null normal K. Then if I take the time derivative of this, that is to say, if I take dk of dh minus dA of dk of h, so it only worries about time dependence of D up here. So that actually is identically zero. So even if you restrict D to the horizontal one forms, it is time independent. And therefore, D is completely determined by its action on the one form, such that it is not horizontal. JB, KB is not equal to 0. Let's just say equal to -1, because it's not equal to 0. You can take any one, because any other one can be obtained by adding to it a horizontal one. And now we can work out D dot, what D dot is, what is the rate of change of derivative operator on the G. And we find that it is related to the omega and the four-dimensional Riemann tensor projected along J and along K, and these two indices are pulled back to the horizon, to the three-dimensional weakly isolated horizon. So the geometry of the horizon, which is really the metric and the derivative operator, is not stationary in general. QAB is stationary, but D is not stationary. Why then can weakly isolated horizons represent black hole horizons in equilibrium for which a zero in the first law hold? Because in these applications, if I looked at this particular thing and expand it out, then the Ricci part of this, when pulled back, is identically equal to 0, but the wild part is not equal to 0. The Ricci terms are 0, but the wild part is not equal to 0. And then it turns out that even though this is not equal to 0, the time derivative is given by fields whose time derivative is 0, which are time independent. So if you like, the D dot in this case, if the Ricci tensor is 0, D dot in this case is time dependent, but its time dependence is rather of a trivial type. So it has time dependence, but of a trivial type. And therefore, D is completely determined by the data that you give on a two-dimensional surface, because D dot is 0. So if I know what D is doing on one surface, more precisely what D is doing on just a one form J, such that J dot K is not equal to 0, then I know what D does everywhere. So therefore, there are no three-dimensional degrees of freedom, or there are no radiative modes. And therefore, if vacuum equations hold, or actually pull back of the vacuum equations to the surface hold, then there's no radiation that falls across H, either gravitational or Maxwell or Young-Mills type, and the first law of the horizon mechanics holds. And therefore, the horizon geometry is said to be, only has Coulombic information determining time-independent shape and spin multiple moments. shape mode, multiple movements are the same as mass, the spin are the same as angular momentum of the horizon. It doesn't have any radiative information. It only has Coulombic information. And that is why it is a horizon in equilibrium. It just can be distorted. It can have angular momentum information, but nothing is happening in time along the horizon. Okay, now what about Scry? Because we say Scry has all this horizon. Scry is also, I claimed, is a weakly isolated horizon. So let us check that. And then explain why is it that there is radiation at Scry. So let's suppose that we have got an asymptotically flat space-time, and now lambda has to be equal to 0 because I would like to look at Scry, which is null, because to be weakly isolated horizon, it has to be null. And then I can look at a conformal completion of it by adding Scry to it, and the conformal metric is just omega squared times GAB, such that omega is equal to 0 at Scry, grad omega is not equal to 0, Scry is topologically is 2 cross R, and Einstein's equation hold on the physical space-time such that omega times TAB admits a limit, so omega, so stationary tensor falls appropriate rate. This is a standard definition of asymptotic flatness. Then this implies Scry is null, and we can always choose omega to make it divergence free. And then conformal Einstein's equation imply that in fact grad of n itself is 0, n is covariantly constant. And therefore, if I take Scry, is a three-dimensional null surface, it is null normal n hat, it has an intrinsic metric q hat, which is signature 0 plus plus. There's a null submanifold of the conformal completion, not of the physical space-time, but of the conformal completion, on which the expansion vanishes. The expansion is this, that vanishes. And therefore, there exists a derivative operator, which can be pulled back, and dA NB is equal to 0, but dA NB was equal to omega times n, because that was the definition of omega. That means omega itself is 0. Since omega is 0, ln of omega is 0 trivially. Therefore, Scry is a null surface on which expansion vanishes, and omega is divergence free, just 0. So it's divergence free. And therefore, Scry is in fact a weakly isolated horizon. At first, it is shocking. I was completely shocked by this. How can Scry be a weakly isolated horizon? Well, because the weakly isolated horizon, how can it have radiation? Well, remember what was the time dependence can come from. The metric is time independent. So in this case, Lie hat of Q hat AB is time independent. And Lie n hat of omega hat is of course time independent because omega itself is equal to 0. So as the derivative operator, its action only on the one form. So in this case, K hat is replaced by n hat, and J hat is a one form, such that J is a one form for which JAKA is equal to -1. And now, because following the convention, usual notation, instead of J, I'm calling it L. So L is a one form such that L hat A, N hat A is equal to -1. So I can evaluate this, and this is the same equation as before that I had, exactly the same equation. But previously, it is this term that survived on a black hole horizon, and this term went away because of Einstein's equations. Now, omega is equal to 0, so this goes to 0, this goes to 0. And because of conformal Einstein's equation and S2 cross R topology, the full wild tensor on Scry is 0, therefore this term is also 0. And therefore, in fact, the terms which survived in the previous case now vanish. And what is left is precisely the term which vanished before. And this term has precisely the information about the Bondi news. So this Bondi news has exactly the 2 degrees of freedom which are radiated. So now the derivative operator here is really it has information about shear, if you like, and that is the radiative data that I got up here. So every term that was non-zero at the black hole weakly isolated horizon because of Einstein's equations now vanishes, and there are no Coulombic degrees of modes freedom. There are no Coulombic degrees of freedom or modes or Coulombic information up here. Now D has only purely radiative modes, and therefore this really is very interesting. This is work with Simone, and I went for a walk. I happened to be listening to Bach, and I suddenly realized that this is a fugue. This is a very beautiful fugue because there's a common theme, which is weakly isolated horizon that gives the subject line. The first part is a black hole non-expanding horizon, which develops it in a certain way, and then Scry comes and develops it in a completely different way, a contrapunctual way, and therefore it actually is same subject is developed in a completely different way, and it's really contrapunctual in a few. And some geometrical, is this same geometrical notion of weakly axial horizon and the same equation for d dot, but because we got the Einstein's equation, we got Coulombic modes, and because we got conformal Einstein's equation, which only have radiative modes. So completely different physics. Here you have got serene equilibrium. This is a theme in the fugue, which is of serene equilibrium. And then here we got dynamics and potential outbursts of energy and momentum. Okay, so now let me come to the last part of the talk, which is, again, I'm changing gears and taking the audience from one thing to another. The first two parts were related, in which I was talking about horizons. The very first part, I was talking about dynamical horizons, which happen to be space-like, and I could look at the constraint equations. In the second part, what I looked was the equations which are either RAB equal to 0 up here, or so this equation, and this equation is the pullback of Einstein's equation on the three-dimensional surface. And if the three-dimensional surface were null, then pull back, in fact, is really the evolution equations. And that is what we're seeing now. Now I want to change gears completely. And I would like to extend the standard initial value formulation using the connection variables of loop quantum gravity. So in the standard formulation, vacuum, and for simplicity, let me just use vacuum general relativity. The initial data, as we saw, was a metric in the extension curvature on a three-manifold sigma. Metric as the signature, and KAB is a symmetric tensor. And we got constraints, namely divergence of K minus KQ equal to 0, scalar curvature of the three metric minus this quadratic combination is equal to 0. This we had seen before already. And we got evolution equations. And let's just put shift equal to 0 for simplicity. Then Q dot is equal to 2 times lapse times KAB, the extension curvature, and K dot is equal to n times Ricci tensor minus a quadratic combination of extension curvature minus a second spatial derivative of the lapse field. So that is what we get up here for the evolution equations. These equations are non-polynomial because the objects that I've written down in red up here are non-polynomial in the basic variables QAB and KAB. The Ricci tensor is non-polynomial. This involves Christoffel symbols, which involves inverse metric, and the inverse metric up here is non-polynomial. And furthermore, this in fact system is only weakly hyperbolic system. And there's a nice review article by David Brown about these systems and comparing this ADM system. This sometimes also called the ADM type of system up here, but I'm only looking at the equations of motion, not Hamiltonian formulation at this moment. Now, what happens with the connection variables in loop quantum gravity? Well, the initial data is completely different. It is really, we could take a three-manifold sigma, and we forget about general relativity for a minute, and we just consider Yang-Mills theory. So we got a connection, which is an SU2 connection. I is an SU2 Lie algebra valued index. A and are always the spatial index, as before up here. There's no metric here. We just have these objects up here. And yet you can write down very simple equations, which, in fact, the simplest equation you can write down, which do not bring any background structures, is that the gauge covariant derivative divergence of E equal to 0. This is the Gauss law. Then if I construct the field strength of this, and I contract with E, contract on the internal indices as well as in the space index, that is equal to 0. And if I take two E's and plug it into FAB, so the A and B indices are saturated, therefore I and J are skew symmetric. So I put here the structure constants of SU2, epsilon ijk, and contract I equal to 0. These are the simplest equations you can write down with these variables that you have given, without any background structure, and which are gauge covariant and diffeomorphism covariant. And then you can use them as Hamiltonians if you like, and from them you can get the evolution equations, or you can start with general relativity, make some canonical transformation, and arrive at evolution equations, which will be this. And A dot is equal to, again, fields I get here are just E is linear in E, and this is at most quadratic in A, and E dot is at most quadratic in A and quadratic in E up here. And this combination is really a generalized gauge covariant derivative by the triplet of vector fields, and the triplet of vector fields is constructed from taking the lapse and multiplying it by E. So the details are not important. The interesting thing is that this has a geometrical interpretation, whereas these evolution equations don't have any interpretation in terms of any lead derivatives on the three manifolds. But here we do have such an interpretation. And this was the work that was done with Madhavan Varadarajan, who is at the Raman Institute. And then the statement is the following, that you can take this to be complex, in which case this will be complex general relativity, but you can impose a reality condition to get the Lorentzian signature. And the reality condition says that if I take E and contract the internal indices with the delta ij, then this object should be real. And similarly, if I take the E dot and I symmetrize and I contract and then contract this object with the internal index up here, this is J. So there should be J here. Then you get again that this should also be real. Again, the point is that all these equations are completely polynomial. All that I got up here on the right-hand side, up here, they're polynomial in this thing. And together, in fact, they form a symmetric hyperbolic system. In order to do that, we only have to add a certain combination of constraint equations to this and choose lapse in a certain way, but you can choose it in a way which does not depend on the background fields themselves. And then the statement is that this is actually a symmetric hyperbolic system. And the constraints and reality conditions are preserved by dynamics, just as in ordinary general relativity, the constraint equations are preserved by this dynamics up here. Now, there is an explicit dictionary which says that if you give me A and E, I get Q and K. And therefore, in this sense, to begin with, I only had gauge fields, and I had a diffeomorphism covariant gauge theory. And from that gauge theory, general relativity is born, because I can give you explicit dictionary to go from A and E to Q and K, and then Q and K satisfy exactly these equations. So one might say, well, these are non-polynomial. These were all polynomial. How can this be? Well, it's because the dictionary, which sends the gauge variables to gauge theory variables to these geometrical variables, is rather complicated. So if you like, one can say that simplicity is really here, but what is useful, what we see normally, is really the variable useful are here. It's a bit like nuclear physics, in which quarks and gluons are simple, nuclei are complicated, but nuclei are much more rich, and therefore we deal with nuclei up here. So this dictionary is a dictionary which brings in the complicated non-polynomial behavior of the equations governing the metric variables. And now the only thing that I want to draw your attention to is that if I take what is this dictionary? So one element of the dictionary is the metric is obtained by just taking E and E and contracting their indices with delta ij. But that doesn't give me a contravariant metric, but it gives me a contravariant metric with a factor of determinant of Q. So if you like, E is like an orthonormal triad, except that it is a density weight 1. So this is what gauge theory variables mean in the geometric language. And then now, the important thing is that the green equations that I wrote down, I never had to lower the index of this or raise the index up here. And therefore, the statement is that these equations are completely well defined, even when the metric becomes degenerate. So if QAB becomes degenerate, as for example, what happens at the Big Bang? At the Big Bang, the 3 metric is conformally flat, but the conformal factor goes to 0. Similarly, the Schwarzschild singularity. If you go inside the Schwarzschild solution, and so this is let me draw the whole solution first. And if I look at the inside the Schwarzschild solution, and if I look at the R equal to constant surfaces, which are space-like, and approach the singularity, then the metric becomes degenerate because R goes to 0. Therefore, the determinant of the metric vanishes. So these are singularities. But at these singularities, these connection variables equations don't break down. You can evolve further. So the symmetric hyperbolic nature of AE, they are also canonical conjugate variables, well suited for non-perturbative condensation and the study of the decayed behavior near singularities. And the reformulation of green equations using density weighted, but you can do a reformulation of this green equation using only density weighted space-time scalars. This is also a big surprise for me. Namely, what you can do is, given A, I can just convert the internal index into a space index. I can remove the space index and convert it into an internal index. And this is complex. Therefore, this will be Cij plus I times Pij. Real part is this, and imaginary part is this. This is like the spin connection of the triad, and this is the extrinsic curvature. And then similarly, I got the spatial derivative operator, and I can convert the index into an internal index. So what happens is that in simple examples like the ones I mentioned, these quantities remain finite at the singularities in these simple examples. Even though it's a singularity, even though the metric blows up, curvature blows up, these quantities remain finite. And you can write down the constraint equations, and I wrote down in gory detail all the constraint equations. And they all only, of course, have only internal indices, and they're all only involve D and P and C. They're either linear or quadratic in these variables up here. And the D dot is, you can write down the D dot equation up here. And these dot equations, C dot and P dot equation, time evolution, they're also linear and quadratic in this C and P and D. And these remain perfectly well-defined at the singularity. Therefore, everything remains well-defined. And you can evolve this D dot with an internal index, this new derivative operator we got. This is not a derivative operator in the usual sense, because this index is an internal one. But we can, its time derivative is really known. And this is just known from the equations that I wrote down about time derivatives of A dot and E dot in this picture up here, A dot and E dot. Therefore, I know this thing. So the statement is that the strategy is that on an initial slice where Q and K are regular, so they're not degenerate, you can introduce these triads and you can construct these variables, Cij, Pij, and Di from E and A, and then evolve the triplet without reference to the metric and the extrinsic curvature of A and E. These variables can blow up somewhere, that doesn't matter. These can potentially remain finite, and they do remain finite at the simple singularities. And therefore, we can simply integrate the ordinary, and at the end of the day, we can just integrate an ordinary differential equations to get what the triad E up here. We can just integrate this thing up here. And so the statement is that for the most of you begin with really what we can begin with Q and K. From there, I can introduce an orthonormal triad and construct this A by formula. I'm not written it down, but you can construct this K, give the triad up here. And then the statement is that I got A and E. And then from there, I can construct these variables. And these variables can be evolved across the singularities. And then when we are on the other side of the singularity, you can reconstruct the E. And therefore, from there, you can take Q, K, E, and A, etc. Now, there's no guarantee that you can always do this across any singularity. But the statement is that the most interesting singularities, the Big Bang and the Schwarzschild, this is true. And so the connection variables extend the predictivity via of the standard initial value formulation, because they don't need the 3 metric to be non-degenerate. So finally, summary and then references. The initial value formulation of Einstein's equation, to which Madame Choquet made pioneering and seminal contributions, is a rich field. And in this rich field, I discussed only 3 aspects of this rich field that emphasize the astonishing interplay between geometry, analysis, and physics. First, I looked at the invariant expression. First, I looked at the constraint equations and dynamical horizons. And then the statement is that we have invariant expressions for gravitational energy fluxes across the dynamical horizons. We have got topological restrictions on the marginally trapped surfaces. And we have a theorem which is increase in area, but now that increase is due to physical processes that we can directly refer to. For the evolution equations of the usual initial value formulation, the horizons of black holes in equilibrium and null infinity, which seem so different from each other, are 2 facets of the same thing. And this is what comes out. And now in this case, we use the evolution equations. But they emerge from the same notion, namely geometric weakly isolated horizon framework. And furthermore, the time dependence of this D on a general weakly isolated horizon. if we actually pull back Einstein's equations to the weakly isolated horizon, then we get horizons of black holes, which are in equilibrium. There are no 3D degrees of freedom, and only Coulombic fields appear. And we can have multipoles and zeroth and first law. Or you can pull back the conformal Einstein's equations to the weakly isolated horizon. In this case, it is Cry. You pull back conformal Einstein's equations up here, and these are precisely gives you the Bondi news. And these are the 2 degrees of freedom per space point. These are the radiative modes and fluxes and bursts of energy, supermomentum and angular momentum. So the two things are dramatically different from each other. And it turns out that there is an astonishing fact that the BMS group of Scry plus BMS charges and fluxes at Scry, they all emerge from the same weakly isolated horizon framework. When applied here, you find that the fluxes vanish. When you apply here, you find the standard flux laws for radiation of energy, momentum, and angular momentum. And the final part is just that the connection variables of loop quantum gravity extends the initial value formulation to include degenerate metrics encountered in some of the most interesting singularities. And in this sense, predictability of classical GR is enhanced even prior to quantization. And also because it is a Hamiltonian framework, one can use non-perturbative quantization. Here are some basic references. As I said, these are not the latest references. Some of them are quite recent, like this year's 24. But the statement is that these are good for you to, those of you who are interested, to get a feeling for, to get started on the topics that I discussed. Thank you very much. Are you online? Hello?
Yes, sorry, Abhay. I was muted by the host.
Okay.
So yes, thank you for an excellent, really excellent talk. I think I in particular learned a lot from your talk, and this is going to be an amazing resource to go back to in multiple ways. So we're going to take questions in the chat box. Please send your questions to the co-host called questions. And we already have a couple, so I'm going to just read them out. These are from, the first two are from Karthik Prabhu. The statement, the question is, there is a result by Sibierski that Schwarzschild is not C0 extendable across the singularity. What does that look like in the C and P variables?
Right. So in this case, so it's not extendable in the usual sense of the word. Certainly, that's true. So C and P variables. There's a master's thesis of Perimeter Institute, which discusses actually this result. But it's not very surprising. If in retrospect, it's really what you expect it to be. The metric actually just looks like basically you got R, right? The R goes to 0, where the metric becomes degenerate. The covariant metric, the 3 metric becomes degenerate then at R equal to 0. The determinant goes to 0. The different components in the Schwarzschild case, they behave differently. But then on the other side of Schwarzschild, you just basically replace R by absolute value of R. Therefore, you just get that in the extension, when I reconstruct the metric, it is just the R goes to absolute value of R. So it's not a very profound thing. It's like, if you just take R goes to absolute value of R, then on the other side, again, you're going to get a Schwarzschild, again, going to get a metric, which is perfectly fine. But the point here is that C and P are okay, and therefore you can actually do this extension. Second question?
Yeah, so there's another question by Karthik. I think we also had, sorry, I just want to tell everybody that in case you're not able to access the chat, please send it to the main group where we were hoping that everybody, I think there was a hand raised and we didn't get to that question. So the second question by Karthik is there an analogous formulation using the connection and triad variables for data on a weekly, weak horizon or null infinity?
Very good. So the connection variable, the usual connection, self-dual variables. In fact, they were inspired by null infinity. And so there is a formulation at null infinity. And those of you know, it's quite an amusing story. It was Gabriela Gonzalez when she was a PhD student. She was a spokesperson of LIGO when LIGO discovered the gravitational waves, and she was in the announcements and so on. But she started her PhD with me in mathematical relativity and quantum gravity. And in fact, one of the first projects we looked at was precisely writing the new variables, writing the description of Scri in terms of new variables. It's just that it's not there's nothing profoundly new about it, because the self-dual variables are very, very well suited at Scri here. For weakly axial horizon, the answer is again weakly axial horizon. Yeah, the weakly axial horizon have been looked at in the new variable context. I think that they have been looked at more not in terms of the self-dual variables, but just four-dimensional connection variables. But it's not difficult to rewrite everything in terms of these connection variables, and it's just that they don't particularly. There's no dramatic simplification, and that is why it is not done in terms of the usual, in terms of the self-dual variables. At Scri there is, but at the weakly axial horizon, general ones, or at dynamical horizons, there isn't a dramatic simplification. But this has not been looked at. So if anybody wants to do it, they should definitely look at it in detail.
We haven't got another question from the participants. So again, encouraging people to send in their questions.
Why don't they just raise a hand and then they can just speak?
Okay, I think it's a small enough thing that we can do that. We've unfortunately muted them, so we can try to unmute.
You can unmute everybody just for the next 10 minutes,
yes,
right?
We can do that. And so can you please, those of you who want to raise your hands and ask questions, please do so. In the meanwhile, let me ask you a very broad question, Abhay, about, in recent times, people have been working a lot on high derivative theories of gravity, where as sort of ways in which you understand renormalization of general relativity and including these high derivative terms and so on. Of course, there is this issue and question which arises always about the well-posedness. So in the purely quantum regime, how do you see this possible, this issue of whether the classical equations are well posed versus the quantum equations perhaps requiring these connections to these high derivative terms, and sort of just a broad question on your opinion on this.
Yeah, so the point is that the quantum theory one is not really evolving. The question is not well posed because what are the classical field equations you have are going to be so you cannot use the evolution. I mean, at least there's no guaranteed stable evolution, right? In the classical theory. But in many of these approaches, one is really interested in something like an S matrix or something like that. And then the state, I mean, it's not the same question as actually evolving through a well-posed system of differential equations. So I think that you could get meaningful S matrices. It's not impossible that one gets meaningful S matrices, even in this case. Whether, I mean, it is the burden on this series to then show that somehow in the classical limit, these higher derivative terms are all insignificant. That usually is the case because they're suppressed by Planck length. And therefore, we just have general relativity where it is well posed. So my statement is basically that I don't see a glaring obstacle in quantum theory for these theories to make sense, because one is not using this field, one is not using the classical, the field equations coming from Lagrangian. One is just doing some path integrals, or one is doing something. So one is not really using the hyperbolic evolution using those higher derivative Lagrangians. And therefore, I think that there's no direct head-on conflict, but it is something that, I mean, typically then, you're there to worry about whether that goes. They have to worry about other questions that come up. But those questions are not, so to say, one-to-one related to the well-posedness of the Cauchy problem for the classical field equations. It's kind of a different set of questions.
Okay, thank you. Thanks, Abhay. Perhaps people are a little shy today. I was hoping
maybe
we
it
have
was
more
too
questions.
Can I
fast.
ask a question, Sumati?
Please,
Yeah.
Tarun, go ahead.
It's somewhat naive, but Abhay, I mean, so the loop quantum gravity part where you talked about the initial value formulation and the fact that you can go past singularity, is that useful in some sense for numerical relativity?
Okay, so the thing is that, I mean, it could be useful, but it's not been used. I think there are two different things. Is it, in principle, can it be useful? And in practice, will it be used in near future? And in principle, it could be useful, but in practice, it's not really used very much in the I mean, even forgetting about the singularity, right? I mean, the statement was that very early on in 2009, people showed, I mean, not very early, but reasonably early, the people showed that it is actually a symmetric hyperbolic system. And so that could have been used at that time in numerical relativity programs, right? In order to do standard evolution of the simulations that people do, binary black hole simulations or anything. But by then, the other formulation, the BSSN formulation, the various other formulations which are based on metric variables, had already been, evolved sufficiently that people thought it was, just from practical point of view, it was easy to just do some little fixes, more and more little fixes, and then go on from there. And then, of course, much later, Franz Pretorius actually, so I said 2009, I mean 1990s, that people had shown that with the connection variables, the system is symmetric hyperbolic. Okay, but in about 2000 and something, 2005, 6, I mean, when Franz Pretorius used completely different framework, not the one that I showed you just now, but in fact the framework which is very much based on Madame Choquet's work, using harmonic coordinates and so on and so forth. That framework gave to stable simulations. So in the classical regime, there's not that much reason to redo the wheel. Maybe it is, I don't know, because it might give a new insights into what does it via connection variables. But at the moment, using the hyperbolic formulations that they have, using the formulation that Franz Pretorius and then other people developed, I think that they are likely to be used in the near future much more than starting from scratch with connection variables. And in numerical relativity, from the practical point of view, there is not that much interest in really going beyond the singularity, right? I mean, because it's not that singularity is resolved. Curvature still blows up, and the tidal forces will still diverge, and the geodesic, deviation vectors will actually still become, there'll be infinite geodesic. Things will be actually torn apart. There's no question about it at the singularity. That's not a problem. But this is all about classical observers, classical probes. Then there is a lot of work that goes on about what happens if you use quantum fields. And there, can you evolve quantum fields across a singularity is interesting question. And that question, on the other hand, people are looking at in some detail, some of them with me. And there, in fact, to go up across singularity, you need a set space-time. So you can use these space-times I talked about, the extension of Schwarzschild space-time or extension of the um, the Friedman Robertson Walker spacetime or certain Bianchi models, Bianchi 1 spacetime, etc. So there people are doing quantum field theory in curved spacetimes, but really evolving the quantum fields across the singularity. So there it is useful.
Thank you. If there are no other question, I can ask another curiosity question. Smriti?
Yeah.
Please go ahead.
Okay. So the other thing is, I mean, of course, your whole formulation of what you call the new variables was to do non-perturbative, approach non-perturbative approach to gravitation. But generally, I mean, the kind of areas I have worked in perturbations of a fixed background. In that context, has anything ever has been done, or things like gravitational waves or cosmological perturbations? Is it interesting thing for a say a undergraduate to do?
Oh, I think it's definitely it is interesting. I mean, I don't expect anything. I mean, in my old book, I had already done the linearized gravity in using connection variables, and you can see very quickly. You can see that I think it might even be in that notes that Sucheta took actually in long time ago.
Okay, no, so I was just wondering. I'm sure some you would have worked.
Yeah, so but that was just linearized gravity of flat space. But I think it might be. I mean, they're likely to be useful also looking at perturbations in cosmology, right? Because they're very well tailored to Weyl curvature, and so curvature perturbations. Background Weyl curvature is 0, and so they'll be very well tailored to that. So I think, so it is worth. I mean, I'm not saying that there is a clear signal that you learn a lot, but it's not something that.
No, as an exploratory thing, and I was wondering how much is.
Yeah. No, I think that is likely to be useful. It's definitely interesting to see what happens in cosmological context or black hole perturbation theory also. I mean, these theories are so well developed that it's very unlikely that you're going to get brand new insight. But certain things might become more clear or more, transparent.
Right. And another question was about this. You had this nice equation where you showed that lambda greater than 0, you have S2 topology for the event horizon, and lambda less than 0, you can have any topology, and lambda equal to 0, you can have S2 or T2. And T2 is a very contrived situation.
Right.
But if you were to do that, I mean, if suppose there is a thing, first of all, then how do things change? I mean, I mean, just as a fun model, has anyone looked at what happens to the quantum field, quantum evaporation or something like that?
Oh, no, I think people had just looked at, Lewandowski in particular had looked at the detailed example with the T2 topology. It's very, very contrived because everything has to be 0 and you have to find it. It's probably not stable, but it was not shown. But so it might be worth looking into it. Again, this is not something that I would recommend as being, leading to great physical insights, because I don't think torus topology really is. These are torus topology of the horizon by itself. Okay? That this torus topology of the horizon really, exists. The lambda equal to 0 case, but I think it's definitely worth seeing, right? I mean, what happens? I mean, as again, undergraduate or a first problem for a graduate student, working out the equations in this case and looking at all the consequences is interesting, and to see if it's stable or not stable, to show that it's not stable is interesting.
And T2 has 0 curvature.
T2 has 0. It is 0 curvature, and therefore the scalar curvature is 0, and therefore this Gauss invariant is also 0. Let me see where it was. Where was it? I was trying to find it. Yeah. So this Gauss invariant is 0. For T2, this I would be 0. But then this term would have to be 0 because it's positive definite. And in the case of this bigger than or equal to 0, the stress-energy tensor times this also would have to be 0. But you could just say there's no stress-energy tensor. So therefore, the conditions are just going to be on geometry, namely both of those things are 0, and what kind of dynamical horizon that is. where both of them are 0. It might be interesting because, yeah, it might be interesting. And particularly the context of, as you were mentioning, the black hole evaporation case or something. In the black hole evaporation case, there is a very interesting case. There's a space. Yeah, there's a space-like surface, which is actually a dynamical horizon. So when the black hole, what happens is that when normally you got this trapped and anti-trapped region, this trapped region right here. This region is trapped up here. So in the loop quantum gravity ideas of a black hole evaporation, you actually can evaporate, and so you can go. This singularity now it is quantum gravity effects. It's not just general relativity. Because of quantum gravity effects, this curvature up here is not infinity, but it's finite curvature. So the metric is actually well defined. The effective metric up here is well defined. There's a finite curvature up here, and you can go from a trapped region to an anti-trapped region. And in the loop quantum gravity case. But then this surface up here is a space-like surface, and on that space-like surface, these quantities are both 0. And so that is an example, for example. But normally what we only always, because the topology here was that of a S2 cross R, we're assuming that the topology here is also S2 cross R. So it might be worth checking if in fact what happens if we, there's a way to look at the T2 topology here. That might be worth checking. So, I mean, as you say, this is a contrived example, but it could actually occur. And it does, this exceptional dynamical horizon does occur at the end of the evaporation process in loop quantum gravity for completely independent reasons.
Thank you.
Okay.
I have one small question before maybe we should wrap up. But I was wondering with this weakly isolated horizon, the link between scribe class and the black hole horizon, there have been attempts at trying to also look for charges similar to the BMS, charges associated with the BMS group. Do you think that this way of sort of putting it into one single formulation in some sense is a useful way going ahead? I'm not sure whether there's already work done in this, but that was the thing that struck me about your presentation.
Yeah. So the statement is that if I look at so the weakly isolated horizon. So these are null. And then the statement is that yes, exactly. That there's a group on this weakly isolated horizon, and this is in the references that I gave. Well, there's the papers. Maybe it's not there. I don't know. There's the papers with Lewandowski and let me say plus Lewandowski. The papers appear just the last couple of years where weakly isolated horizon and symmetry groups are worked out. And there is this paper which just is going, one paper which came out last month and another paper, detailed paper with Simone Speciale, which is coming out. The detailed paper is coming out tomorrow, I think, or maybe on tomorrow is Thursday. Yeah, either Thursday or Friday, it's going to come out. This paper up here, this has to do with precisely the questions you're asking about, scry and the horizons. And it turns out that on this weakly isolated horizon, you also have a symmetry group. And this symmetry group, this is really a one-dimensional BMS group, extension of the BMS group. So it's a semi-direct product of the BMS group with a group of dilations. This is one dimension. And therefore, there are charges associated with this symmetry group here on the horizon. And there are charges associated at infinity with also the BMS group up here. So the construction is very similar in the two cases, but of course, physics is very different. In this case, you got charges are getting radiated away. In this case, if it's a weakly isolated horizon or perturbed weakly isolated horizon, then the multiple moments are changing. It turns out there's a work with Neil Kera, which shows that this is not quantum, this is classical, that we got black hole mergers, then we got a dynamical horizon that is forms, and that, so this is a dynamical horizon up here, and that becomes a non-expanding horizon or the weakly isolar horizon in the distant future. But there is still some radiation falling up here, and so therefore it is perturbed weakly isolated horizon in the distant future. And then here you got scry, and this is really the question you're asking. And then I got, I can consider hyperboloid slice up here, which connects the two. And people look at, this is the quasi-normal mode region. And then the statement is that you can relate the charges up here with what is happening at infinity. And in fact, in the simple case, in the case when the final black hole is actually settling down to a Schwarzschild black hole, then there's a one-to-one correspondence between multiple moments, the change of multiple moments here, these are the charges, if you like, and the supermomentum flux up here. And so therefore, there really is a relation between the two things in this case. If the final black hole is Kerr, the relation is obscure, is much more complicated, so you don't see the complete detail, but in the Schwarzschild case, one sees the detail. So the answer to your question is yes, there is a relation. There are going to be relations between the observables at the perturbed or non-expanding horizons up here, perturbed non-expanding horizons, and between sclar. And I think that is a fertile area in which a lot of people are working.
Oh, that's really interesting. Thank you. Thanks. I'm
Yeah,
going to
what I
check
talked
one
about
second.
is in some sense, much more to do with the differential equations part. In what I talked about is somewhat elementary. The geometry and physics interface is the non-trivial part. And there are other talks. I think the differential equation part will be very beautiful results in the differential equation parts will show up. I think I saw that Mihalis and Lydia Bialis, the Formas and Lydia Beery were in the audience, and they will, for example, talk about much more rigorous work using analysis. And what Madame Choquet had this book, right, which was manifolds analysis and physics, analysis, manifold, and physics. So I was more about the manifolds and physics. They will talk about more on the manifolds and PDEs and analysis.
There's actually one more question that's come in, which is, does the non-degeneracy at singularities using loop quantum gravity suppose a naked singularity? This is by Scott Shaw. Scott, if you want, you can raise your hand and ask the question in person or clarify.
So, okay. So this is not the issue of, we use only loop quantum gravity variables, right? These connection variables, which are used in loop quantum gravity. But it's really, classical theory, classical general relativity. If you like, it's an extension of classical general relativity, you're right, because classical general relativity just doesn't allow degenerate metrics, whereas these connection variables allow degenerate metrics. So it's not a naked singularity because it's still space-like, it's not time-like. And so if you extend this and go to the other side, then the statement is that, yeah, so good question. Okay. So it will be, normally I got, normally what I would have is a Schwarzschild space-time. So I just have I have a Schwarzschild space-time. And what one is doing is one is taking this part of the Schwarzschild space-time, just focusing on this part, and saying that I can extend the fields across here. And then when I've done that, I will get fields. I'll get an extension. Oops, let me just do this better. I will get an extension here. Okay. And then it is true that this singularity that we had up here, in classical theory, this is still a singularity. In loop quantum gravity, as I was saying before, it is not a singularity because there's finite curvature there. But in classical relativity, there's still a singularity as far as the curvature tensor is concerned. But you can evolve these variables across and you'll get some. So here you got some surfaces. Here you'll get subsurfaces. You'll get things like that. And then the statement is that in this region, this is a naked singularity because I can just look back and see that there is singularity. But that's not very different from what happens with the Big Bang. The Big Bang singularity is also naked singularity, right? Here is a Big Bang and then a singularity. And we are here somewhere. And our past light cone, if you just go forever, they will actually intersect the Big Bang singularity. So this singularity here to this region is in the future region is naked. It is space-like. It's not time-like. It's space-like. And but the statement is that because we got differential equations which tell you how to go unambiguously, spurious things cannot come out of that singularity. If you believe, if you use those differential equations, what comes out up here is actually is determinant, and therefore you have got predictability. That is not sacrificed. So if it is naked singularity, just like the Big Bang singularity is a naked singularity, and we are somewhere here, and then we have these surfaces going like that, and we go from one cosmological slice to the next cosmological slice without worrying about, because we know that nothing is spurious is coming out of it. Whatever has happened. So if I can give myself initial data here is a regular initial data, and I can evolve it. Similarly, here there's a regular initial data, and I can evolve it, and there will be nothing spurious happening. Have I answered your question?
Scott, do you want to? Okay, great. Yes. So I think that we don't have any other questions.
Yeah, it's quite late also. So
yes, it's very late for you. Thank you, Abhay. I mean,
no,
I
for
know
you
that
also, right? Because you have a science day, and you probably have
yes,
to
no. That's we're not involved in that.
Okay.
At least a couple of us who are organizing it are not. But thank you so much for staying awake and also for agreeing at this very short notice to inaugurate our meeting. In fact, really deeply appreciate it, and looking forward to seeing you in person, not in the too distant future.
Yeah,
So thank
yeah,
you
it
all
was,
for being
as I
here.
mentioned to you, this last few weeks were extremely hectic for me, but I was very happy to spend some time preparing this talk, both because of this enormous admiration I got for Madame Choquet, and also because of the friendship that I got with Raman Institute, which goes back, as you mentioned, many, many decades. So thank you very much, and thank you for the audience for staying. Okay, bye now.
Thanks.
Okay.
Bye. So we'll close the meeting now. And for those of you who are going to be coming for the other parts of the meeting, 2 o'clock Indian Standard Time, there are 2 talks, start at 2 o'clock. And then later in the evening, for those in North America, 7:45 Indian Standard Time. Please look at the website for all the details. And we'll still be using the same Zoom link for the rest of today, and we'll send out a new Zoom link to the participants tomorrow. Thank you all for being here, and thanks to the other organizers as well, and to Tarun, despite his busy schedule, for being present through the talk. So please, good night, Abhay, and good day to everybody else.
Okay, bye now.
Thanks, Sumati.
Bye.
Thanks, Abhay. Thanks
Okay,
for
you're
taking
very
it up.
welcome. Yeah. Okay, bye-bye now.
Bye. See you. Thank you. Thanks.